Hello and welcome to lesson number 30, the binomial expansion. This lesson is going to be shorter than most since we only have a single formula to talk about, and that formula is this formula right here, the binomial expansion. It states that a plus b when raised to some power n is equal to the sum of terms from r equals 0 up to n of n choose r times a to the power of r times b to the power of n minus r, for n being an element of the positive integers inclusive of 0, where this n choose r term, this n choose r here, is equal to n factorial divided by r factorial times n minus r factorial. If you want to learn more about the choose function, click this video on the top right here. This expression, the binomial expansion, is the generalization of multiplying a plus b by itself a certain n number of times. In earlier grades, you would have learned that if you consider just a plus b times a plus b, as in a plus b squared, you would have learned that a plus b squared is equal to a squared plus 2ab plus b squared. You would have likely done this by considering a plus b times a plus b and then expanding them out and then using the distributive property to distribute a plus b into the a plus b, and finally writing it all out as a squared plus 2ab plus b squared. In later grade, you would have also probably done a plus b whole thing cubed, and either by distribution or some other method, you would have found that this is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. What the binomial expansion allows us to do is to write sums like this for any a plus b to the power of any n. We could write a plus b to the power of 4, a plus b to the power of 5, and so on for any n that is greater than or equal to 0. Another thing we can see is that due to the relationship of the function n choose r with Pascal's triangle, if we consider the coefficients and consider the relationship with the triangle that goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1, and so on, where each term in this triangle is the sum of the term that is above it and to the left of it, and the term that is above it and to the right of it, we can see that for a plus b squared, the expansion of a plus b squared is a squared plus 2ab plus b squared, or more specifically 1a squared, 2ab, and 1b squared, 1, 2, 1, which is this line of Pascal's triangle. If we consider the next expansion of a plus b cubed, we can see that a plus b cubed is 1a cubed, 3a squared b's, 3ab squareds, and 1b cubed, matching up with this line of Pascal's triangle. This is of course because the relationship of Pascal's triangle and this is that if we label these rows as n, and if we label the elements from left to right based on r's, as in r equals 1, r equals 2, and so on, then each element becomes n choose r. Using this, we can see that if we consider the next row, it is 1, 4, 6, 4, 1. And due to that, if we consider the next power, as in power of 4, if we consider a plus b to the power of 4, the coefficients of the terms here are going to come from Pascal's triangle, and they're going to be 1, 4, 6, 4, and 1. As for the actual terms, we can find the actual terms based on the binomial expansion formula. In the formula, we can see that we have n choose r times a to the power of r times b to the power of n minus r. Note that if you consider adding the two powers of a and b here, r plus n minus r is equal to n, meaning that the sum of the two powers of a and b in this expression will always be equal to n. If we consider the variation of r and the variation of these two terms, we can see that r goes from 0 up to n, meaning that the power of a goes from 0 up to n. So it goes a to the power of 0, a to the power of 1, a to the power of 2, and so on. Similarly, since we know that the sum of the powers of a and b are equal to n, we can see that b will have a power of n when a has a power of 0. b will have a power of n minus 1 when a has a power of 1. b will have a power of n minus 2 when a has a power of 2, and so on. Now, using that, we can see that if we consider all of the terms here, we are going to first have a power of a which is going to be 0 or n. In this case, as I've drawn for the above two patterns, we've started with a's power being the highest power. So let's start here with a's power being the highest power. In the first line, a's power is going to be equal to n, which is going to be equal to 4. So it's going to be a to the power of 4 times b to the power of n minus 4, which in this case is going to be 4 minus 4, which is 0. So therefore b's power here is 0, and anything to the power of 0, when that thing is not equal to 0, is going to be 1, meaning that 1 times a to the power of 0, a to the power of 4 times b to the power of 0 is just going to be 1 times a to the power of 4. Now, the next term here is going to be 4 times a to the next power, which is going to be a to the power of 4 minus 1, so a to the power of 3, times b to the power of that number, which is going to be b to the power of 1. The term after that is going to have 1 less power of a, so it's going to be 6 times a to the power of 2 times b to the power of n minus 2, which is going to be 4 minus 2, which is going to be 2. So therefore the next term is 6a squared b squared. The term after that is going to have 4 times the next power of a. We are going from a equals 4, a to the power of 4, a to the power of 3, and then a to the power of 2. So the next term is going to have a to the power of 1, and it's going to have b to the power of n minus 1 or 4 minus 1, which is going to be 3. So therefore we have b to the power of 3. And finally we have 1 times the next power of a. In this case a is going to have a power of 0, since the previous term it had a power of 1. A to the power of 0 is 1, so we'll ignore it. As for b is going to have the power of n minus 0, which in this case is going to be 4 minus 0, which is going to be 4. So we have a last term of b to the power of 4. In general, you can see that if we have a power of n and we have a plus b to the power of n, then a plus b to the power of n is going to start with a to the power of n, it's going to end with b to the power of n, and you're going to have a bunch of terms in the middle that can be found using Pascal's triangle. You can find the coefficients using Pascal's triangle, and you can fill in the gaps by just going down 1 each time in terms of the power of one coefficient, and then go up 1 each time for the other one. In this case, we can see we have a to the power of 4, we go down by 1, a to the power of 3, we also go up by 1 for b. Here b is b to the power of 0, so we get b to the power of 1. We go down 1 for a, so a squared. We go up 1 for b, so b squared. And then we go up, down 1 for a, so a to the power of 2 becomes a to the power of 1. We go up 1 for b, so we get b cubed. And finally, we go down 1 more for a to the power of 1 minus 1 becomes a to the power of 0. And b to the power of 3 plus 1 is going to be b to the power of 4. Now that we've covered the basics of the binomial expansion, let's move on to how it will be used within the exam. So within the exam, what you will be expected to do first off is to remember the binomial expansion. You will be expected to remember the binomial expansion and write it down. Then what you will be expected to do is, for a given certain situation, as in for a certain value of a, for a certain value of b and a certain value of n, you will be expected to substitute into the binomial expansion, which is just easy. You just substitute the values of n, the values of a, and the values of b. The next thing you will be expected to do is to write down the general term, as in the common term. The term in terms of r like this. So without the sum, just the term. So in this case, the term is going to be n choose r times a to the power of r times b to the power of n minus r. You would be expected to write it with n substituted, a substituted, and b substituted. The next thing you'll be expected to do, of course, is going to be substituting each value of r into this expansion, and by doing that, writing down each of the terms. You may be asked to write all of the terms or just some of them, as in you may be asked to write all the terms from r equals 0 up to n, or maybe just r equals 0 up to 2 or something like that. The next thing you'll be expected to do is to find the coefficients of certain terms within your expressions. We'll be looking at that in the future. So let's go down and do some simple examples first off to get a feeling of how we will be applying the binomial expansion to these kinds of questions. So here first off we have a specific example where we have x plus 2 to the power of 5. Here we can see we can easily identify a, b and n. In this case, a could be taken as x, in which case b would have to be taken as 2, and in which case n is 5. So we have n equals 5, a equals x, and b equals 2. Now what we can do is apply the binomial expansion to this and write that this is the sum from r equals 0 up to n, which in this case n is 5, so up to 5, of n choose r, which is going to be n is 5, so 5 choose r, times a to the power of r, so that's x, so it's going to be x to the power of r, times b to the power of n minus r, and b is 2, is going to be 2 to the power of n minus r, where n is 5, so 5 minus r. That is the first thing you're expected to do, so substitute. Next, in order to evaluate this, we're going to need to substitute each value of r into this expression and write down each of the terms. So let's do that. The first term is going to be the term when r is equal to 0, which is going to be 5 choose 0, so 5c 0, times x to the power of 0, so x to the power of 0, times 2 to the power of 5 minus 0, so it's going to be 2 to the power of 5. The next term after that is going to be the term when r is equal to 1, so it's going to be 5 choose 1, times x to the power of r, which is 1, so x to the power of 1, times 2 to the power of 5 minus 1, so 2 to the power of 4. The next term after that is going to of course be 5 choose 2, x to the power of 2, 2 to the power of 3, and I'm going to write the rest of them real quick. And we can see we have written a total of 6 total terms. We have n to the power n being equal to 5, and we've written 6 total terms as expected. If you go from r equals 0 up to 5, you're going to count 6 numbers. Here the next thing we're going to need to do is to evaluate n choose r for each of these values. We're going to have to evaluate 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, and so on. For this, we can use Pascal's triangle. You could do it the old-fashioned way by just substituting n factorial, r factorial, and n minus r factorial and then solving it, but this is an easier way. So if we consider the Pascal's triangle, we need to go all the way down to the column where we have 5 as our row number. So we start with the 0th row, which is just 1, and then 1, 1, 1. The central one is 2, because it's 1 plus 1 is 2, and then 1, and then 1. 1 plus 2 is 3, 3, 1, 1, 4, 6, 4, 1, and the next row is going to be 1. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1. These are the coefficients we want. We can see there are 6 total coefficients, which means it is the one corresponding to n equals 5, row 0, row 1, row 2, row 3, row 4, and row 5. So now we can see that the coefficients here are 1, 5, 10, 10, 5, and 1 for 5 choose 0, 5 choose 1, 5 choose 2, and so on. So if we write those down, we can see that our numbers here are going to be 1 times x to the power of 0, which is 1, times 2 to the power of 5, which is 32. So times 32. The next term here is going to be 5 choose 1, which is 5, times x to the power of 1, which is x, times 2 to the power of 4, which is 16. So times 16. The next term after that is going to be 5 choose 2, which is 10, times x to the power of 2, so x squared, times 2 to the power of 3, which is 8. So times 8. The next term after that is going to be 5 choose 3, which is again, as we saw, it's 10 times x to the power of 3, so x cubed, times 2 to the power of 2, which is 4. So times 4. The next term after that is 5 choose 4, which is 5 times x to the power of x to the power of 4, so 5 times x to the power of 4, times 2 to the power of 1, so times 2. And the last term is 5 choose 5, which is 1 times x to the power of 5, times 2 to the power of 0, which is 1, so times 1. Now, if we simplify all of this down, the first term is just 1 times 32, which we can write as 32. The next term is 5 times x times 16, which is 80x, so we can write that as 80x. The next term of that is 10 times x squared times 8, which is just 80x squared. 80x squared. The term after that is 10x cubed times 4, which is going to be 40x cubed. The term after that is 5x to the power of 4 times 2, so 10 x to the power of 4, and finally we have 1 times x to the power of 5, so we have just x to the power of 5. So this right here is the expansion of x plus 2 to the power of 5. Now the questions you could be asked are to either write this thing as in the sum that is equal to write the common term, which in this case would be this thing here, 5 choose r times x to the power of r times 2 to the power of 5 minus r. You could also be expected to write each of the individual terms or certain terms. So you could either be expected to write in this form, like this form where you have directly substituted 5 choose 0, 5 choose 1, and so on, or you could be expected to write them in this form, in which case you have to do some solving in order to get here. So you could be expected to write in either of these ways. So you need to basically know the whole process, because obviously in mathematics you generally need to know the whole process in order to solve these kinds of problems. So we'll do one more and then continue to some exam questions that use this concept. So the next one we have actually has something interesting going on with it. It is 1 minus x to the power of 7. We can see that there's something interesting because instead of a plus, we have a minus. We have 1 minus x. Now normally we have a plus b to the power of n. In this case we have a form of a minus b to the power of n. So in order to use the binomial expansion, what we need to do here is to convert this into the form of a plus b to the power of n. Doing so, we can see if we convert this into the form of a plus b to the power of n forcefully, we get 1 plus negative x to the power of 7. So now we can see if we want to apply the binomial expansion to this, we need to apply it taking a as 1, b as negative x, and n as 7. So that's exactly what we're going to be doing here. So let's apply the binomial expansion now. Next thing we're going to do is to write this as being equal to the sum from r equals 0 up to n, which in this case is 7, so up to 7, of n choose r, so 7 choose r times a to the power of r, which is going to be 1 to the power of r, which I can write here, but I'm going to ignore in the next step, since 1 to the power of r is equal to 1 no matter what r is. And then we're going to have b to the power of n minus r, which is going to be, remember, b is minus x, so we have to write minus x to the power of n minus r, so 7 minus r. Now, what we need to do in order to get all of the terms here is to substitute each of the values of r from r equals 0 up to r equals 7 into this expression here. Now, as I said, I'm going to ignore the r 1 to the power of r, since 1 to the power of r is equal to 1 no matter what r is. So then, our terms here are the value of this when r is equal to 0, which is going to be 7 choose 0 times 1 to the power of r, 1 to the power of 0 is just 1, times negative x to the power of 7 minus r, which is negative x to the power of 7. So we have times minus x to the power of 7. And then the next term after that is going to be the term where the r is equal to the next value, which is r is equal to 1. So we have 7 choose 1 times 1 to the power of r, which is just 1, times negative x to the power of 7 minus 1. So we have minus x to the power of 7 minus 1. I can actually directly write that as 6 since it's not that complicated. So we'll just write it as 6. And then next we have plus the next value, which is r equals 2. So we have 7 choose 2 times negative 1 to the power of 2 times negative x to the power of 5. I'll write it directly as 7 minus 2, which is 5. So times to the power of 5. And then the next term after that is going to be 7 choose 3 times negative x to the power of 4. The term after that is going to be 7 choose 4 times minus x to the power of 3. The next term after that is going to be 7 choose 5 times minus x to the power of 2. The last two terms are going to be 7 choose 6 times minus x to the power of 1. And finally, 7 choose 7 times minus x to the power of 0. So these are the terms that we want. Now what we need to do is to find each of these values of 7 choose 0, 7 choose 1, 7 choose 2 and so on, and write them down into here, substituting them, find our final answer. So going to Pascal's triangle, if we consider the next rows of Pascal's triangle up here, this is the 5th row, and what we want is the 7th row, since we have 7 choose 0, 7 choose 1 and so on. Considering this, if we construct the 6th row, it's going to be 1, then 6, since 1 plus 5 is 6, 5 plus 10 is 15, so 15, and then 20, 15, 6 and 1, and the 7th row, the row that we want, is going to be 1, 7, and then 6 plus 15 is 21, and then 35, 35, 21, 7 and 1. So we have the numbers that we want. We want 1, 7, 21, 35, 35, 21, 7 and 1. Going down here, if we start substituting those in, for the very first term, we have, we have 7 choose 0, which is 1. So we have 1 times negative x to the power of 7. Now, a negative number to an odd power is going to be still negative. Due to that, negative x to the power of 7 is going to be negative x to the power of 7. So we have negative x to the power of 7 times 7 choose 0, which is 1. So we have negative x to the power of 7 as our first term. As for the next term is 7 choose 1, which is 7, times negative x to the power of 6. And a negative number raised to an even power is going to be a positive number. So therefore, this is going to be x to the power of 6. Or rather, I should say, to specify, positive x to the power of 6. So we have 7 x to the power of 6 and it's plus. The next term after that is going to have odd power for the negative number. So it's going to be minus. We're going to have 7 choose 2, which is 21, times negative x to the power of 5, which is going to be negative x to the power of 5. The next term after that is going to be 7 choose 3, which is 35. It's going to be a positive number since the power of the negative number is even. So we have plus 35 times negative x to the power of 4 is just x to the power of 4. The next term after that is 7 choose 4, which is 35, times negative x to the power of 3. Negative x to an even odd power rather is going to be negative. So negative x to the power of 3 is negative x cubed. So we have negative 35 x cubed. The term after that is going to be 7 choose 5, which we know is 21. It's going to be plus, since the power of negative x is even. So we have plus 21 times x squared. Finally, for the last two terms, 7 choose 6 is 7. So we have 7 times negative x to the power of 1, which is negative x. So we have minus 7x, and finally 7 choose 7 is 1, and negative x to the power of 0 is also 1. So we can see that 1 minus x to the power of 7 is minus x to the power of 7 plus 7x to the power of 6 minus 21x to the power of 5 plus 35x to the power of 4 minus 35x to the power of 3 plus 21x squared minus 7x plus 1. We can see here that when we have a negative in our binomial expansion, our terms have alternating signs. We have minus x to the power of 7 plus 7x to the power of 6 minus 21x to the power of 5 plus minus and so on. If we had more terms, we would still have this plus minus format. Something interesting happens, however, if both terms are minus. If both terms are minus, something else happens where if this power here is even, then all the terms have the same sign and all the terms are positive, and if this power here is odd, then all the terms have the same sign and all the terms are negative. If of course both terms are positive, then we just get all positive terms. So we can see in general, if both of these terms are positive, then all the terms are positive. If one of them is negative, then we get an alternating sum where one is positive, one is negative, one is positive, one is negative. And if both are negative and we have an odd power, all terms are negative. But if we have both negative and an even power, then all the terms will be positive. So now finally, let's apply all the knowledge we've accumulated so far into an exam question. Here we have the 2024 A-Level Combined Mathematics Paper 1 Part A question number 4. Now question number 4 might look intimidating or complicated compared to all the stuff we've been doing so far. That's because all the stuff we've been doing so far has been simple and just involving the binomial expansion. However, here we have a little bit more than that. We also have some logic to apply. But this question is actually not all that complicated compared to our questions that we had above. So let's go to the question. The question is asking us to show that the constant term in the expansion of 1 plus x cubed times x minus 1 over the square root of x to the power of 9 is equal to 93. Now in this context, what they're asking for, the constant term, just means the term that does not have an x in it, or it has a power of x equal to 0. It's the constant term relative to x. Now here we have to assume that, since they haven't explicitly stated it, however, x is a variable, we have to assume that, and given that, we want the term that does not have an x, in which case, we just want the term that has an x to the power of 0. So given that, what we're looking for here is, in the expansion of this, what is the value of the total terms that have x to the power of 0 in them. So in order to do that, what we're going to do is to consider this thing and expand it. In this case, we can say that this thing is a simple function here. We just have 1 plus x cubed. This thing, on the other hand, is x minus 1 divided by the square root of x all to the power of 9, which means that this has not yet been expanded. This can be expanded into a bunch of terms. So what we're going to do is to expand this into a bunch of terms and then consider multiplying all of those terms with this bit here, and considering that, try and find all the terms that have an x to the power of 0 in them. So doing that, what we're going to do for our solution is to first write that we're going to consider the second bit, which is x minus 1 divided by the square root of x to the power of 9. The reason we're doing this is the fact that this bit is the only bit that we need to expand. This bit here is already expanded. So if we expand this thing, we can see that x minus 1 divided by the square root of x could be written as x plus negative 1 divided by the square root of x and then to the power of 9. Now we have the form of a plus b to the power of n. Doing that, we can now substitute the binomial expansion into this. The binomial expansion for this thing is going to be the sum from r equals 0 up to n, which in this case is 9, so up to 9, of n choose r, so 9 choose r, times a to the power of r, in this case a is x, so we have x to the power of r, multiplied by b to the power of n minus r. In this case, b is negative 1 divided by the square root of x. This is important, this distinction, that this is negative. So we have minus 1 divided by the square root of x, all raised to the power of n minus r, which in this case is 9 minus r. So this right here is the sum of all the terms that come out of this thing right here. This x minus 1 divided by the square root of x to the power of 9. What we can do now is to simplify this thing and eliminate this bit here and this bit here and just write it as x to the power of a single number. We can do that because right here we can see this is just x to some power, and in here we can see we have a minus to some power, and we also have the square root of x, which 1 divided by the square root of x rather, which is just x to some other power. So we can actually, using index rules, simplify this down to x to some power multiplied by x to some other power, which we can simplify to just x to the power of a single number. So doing that, if we write this down, this is equal to the sum from r equals 0 up to 9 of 9 choose r. What we're going to do here first off is to take this negative outward as a negative 1 to the power of 9 minus r. So what we have negative 1, actually we'll write it on the front here, so minus 1 to the power of 9 minus r, and then what we're left with is an x to the power of r and this bit here, and we know that 1 divided by the square root of x is just x to the power of negative half, so we have x to the power of negative half raised to the power of 9 minus r. Now when we have something like this, we know from index rules that this is going to simplify into x to the power of negative half times 9 minus r. Due to this, we can simplify this to be equal to the sum from r equals 0 up to 9 of 9 choose r times negative 1 to the power of 9 minus r times x to the power of r times this bit, which is going to be x to the power of negative 9 minus r divided by 2. The next thing we can do is to use index rules to fuse these two together. We can see we have x to the power of r here, and we have x to the power of minus 9 minus r divided by 2 here. If we fuse these together, we can see that we have the sum from r equals 0 up to 9 of 9 choose r times negative 1 to the power of 9 minus r times x to the power of, when you multiply 2 together like this, we have r minus 9 divided by 2 minus negative r divided by 2, which is going to be plus r divided by 2. So this is going to be the power that we have here. If we simplify this down, this r and this r divided by 2 give you 3r divided by 2. So what we have here is just 3r divided by 2 minus 9 divided by 2, which I'm going to simplify into 3r minus 9 divided by 2. So therefore, this is the common form of each term given by x minus 1 divided by the square root of x to the power of 9. What we want, however, is to multiply that by 1 plus x cubed. So that's exactly what we're going to do, but we're going to do it using this expression here. So if we do that, we have 1 plus x to the power of 3 multiplied by x minus 1 divided by the square root of x to the power of 9. Now if we evaluate this, we can see that this is just 1 plus x to the power of 3 multiplied by this bit over here. So we can take this sum, we can actually copy and paste it right in, substituting it for our expression over here. So if we do that, we can see that what we have now is just 1 plus x cubed times all of this. We can see that we can actually distribute this 1 plus x cubed into this sum here. We can do that by the fact that if we consider the 1 times this sum is just this sum, and x cubed times this sum is going to be the sum from r equals 0 up to 9 of 9 choose r times negative power 1 to the power of 9 minus r times x cubed times this thing here, and it's not going to be a problem since x cubed is a constant with respect to r. So if we do that, we can see that our sum here, our product here rather, is equal to the sum from r equals 0 up to 9 of 9 choose r times negative 1 to the power of 9 minus r times x to the power of 3r minus 9 divided by 2 plus this same sum multiplied by x cubed, which is going to be the sum from r equals 0 up to 9 of 9 choose r times negative 1 to the power of 9 minus r times x to the power of 3r minus 9 divided by 2 times x to the power of 3. Now once again, using index rules, we can see that if we add those two together, we multiply them, we have to add their indexes, which means we have 3 plus 3r divided by 2 minus 9 divided by 3. Now 3 is 6 divided by 2, and using that we can see that our index here is going to be 3r divided by 2 minus 9 divided by 2 plus 6 divided by 2. If we cancel those out, we can see that we're left with minus 3 divided by 2. Due to that, what we have here is going to be x to the power of 3r minus 3 divided by 2. This is going to be the power of our x if we consider multiplying x cubed by this term here. Now that we have that, we can see that we have two sums that sum together to give our total sum, which is the sum that equates to this product here. Now, if we consider the question is asking us to find the constant term of the expansion. In that, we know the constant term is just the term where the power of x is equal to 0. Now, if we consider this bit here, we have two sums. This sum could potentially give a power of x equal to 0, and this sum could also give a term where the power of x is equal to 0. What we're going to do now is to consider the value of r in this sum required to get a power of 0, x to the power of 0 from this sum, and we're going to consider the power of r required to get an x to the power of 0 in this one as well. Considering the first sum, we can see that the common power of r is x to the power of 3r minus 9 divided by 2. Therefore, if we want this thing to output a constant term, this 3r minus 9 divided by 2 needs to be equal to 0. So to find the r that will give that, we can just do 3r minus 9 divided by 2 equals 0. If we solve this, we can see that if we multiply both sides by 2, we get 3r minus 9 equals 0, leaving us with 3r equals 9, and finally r equals 3. So therefore, for this particular sum, at this particular sum's value of r equals 3, we are going to get a constant term. Similarly, if we consider this other sum, in this sum, in order to get x to the power of 0, we need this thing here, this bit, to be equal to 0. So we need 3r minus 3 divided by 2 to be equal to 0. If we write that down, 3r minus 3 divided by 2 equals 0. If we take this 2 to the other side, we can see that 3r minus 3 is equal to 0, meaning that r minus 1 is equal to 0, and thus r is equal to 1. Now note, this r here, r equals 3, that gives a constant term from this sum, is not the same as this r equals 1 that gives the constant term from this sum. They are two different r's because this r is only relevant for this thing and this r is only relevant for this thing. So don't think that r equals 3 in this sum will also give you a constant term. It won't. It will only give you a constant term in this sum. If we wanted to avoid this, we could have just put like k as the counting variable in this one or something, but I'll just use r because that's the most common thing. So now we can see for r equals 3, this sum gives a constant term, and for r equals 1, this sum gives a constant term. If we want the total constant term, we just need to add those two constant terms together. So if we consider the first term, the first constant term that comes from here, I'll write that down here as the first constant term. This term is the term that comes from r equals 3 in this first sum. Substituting r equals 3, we can see we have 9 choose 3, so 9 choose 3 times negative 1 to the power of 9 minus 3, so negative 1 to the power of 9 minus 3 times x to the power of 3r minus 9 divided by 2, which is going to be x to the power of 3r is going to be 9 minus 9 divided by 2. If we simplify this down, 9 choose 3 is going to be 9 factorial divided by 9 factorial divided by 3 factorial times 6 factorial. Negative 1 to the power of 9 minus 3 is going to be negative 1 to the power of 6, which is going to be negative 1 to an even power, which is going to be 1. And then for this bit, x to the power of 9 minus 9 divided by 2 is x to the power of 0, which is just going to be 1, so times 1. So therefore, the first constant term is this thing here. If we consider this thing, 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. We can see that all the terms in 6 factorial cancel with most of the terms in 9 factorial, leaving us with just the leading terms of 9 times 8 times 7. On the denominator, we have 3 factorial, and 3 factorial is equal to 6. So we have to divide by 6. Then times 1 we can cancel off. So therefore, the answer here for the first constant term is 9 times 8 times 7 divided by 6. If we cancel the 3 here, we can get 3. If we cancel the remaining 2 with this 8, we can get 4. 3 times 4 is going to be 12, and 12 times 7 is going to give us 84. So therefore, the first constant term, not 34 rather, 84. The first constant term is 84. Now as for the second constant term, if we consider the second constant term, this term comes from the second sum when r is equal to 1. If we substitute 9 choose 1 times negative 1 to the power of 9 minus 1 times 3 times x to the power of 3r, or 3 times 1 minus 3 divided by 2, we get 9 choose 1 times negative 1 to the power of 9 minus 1 times x to the power of 3 minus 3 divided by 2. 9 choose 1 is going to be 9, so we can just directly write that as 9. If you want, you can do the 9 factorial, 8 factorial, 1 factorial thing. It's going to be 9. times negative 1 to the power of 9 minus 1 is going to be negative 1 to the power of 8, which is an even number, so therefore it's going to be positive 1. And x to the power of 0 is going to be 1, so therefore that's just 1, leaving us with just 9. So the first constant term is 84, the second constant term is 9, therefore the total constant term, which we can just write as constant term, is equal to 84 plus 9, which is equal to 93. Hence we have shown, as the question said, that the constant term is equal to 93. Now some of these steps you can skip or streamline when you're doing your actual solution, but this is just a solution that I created so that I can better explain to you what you're supposed to do. You could skip some of these steps, you could make your notation simpler, you could even just take the general term instead of doing this sum, like you can save a couple of seconds by not writing this sigma, for example, but that's up to you. I'm just going to give you the solution and tell you how you can solve it. So, for solving questions like this, the best thing to do is to practice. Just get a bunch of past paper questions and practice them and solve them. You can additionally just write some random terms of the form a plus b to the power of n and try solving them to get a better grasp of the binomial expansion in general. So that's going to be the end of this video. Thank you for watching and goodbye.